So today we have to do what? We have to study about the concept of setup time and hold time. Okay, setup, what is setup time, what is hold time? So first let us see what is setup time. So what do you understand by this name setup? So what are you basically setting up over here? So what do you think? See, basically, if you read what I have written over here, setup time is the minimum amount of time before the active clock edge during which the flip-flop input should be stable to be considered as input. Okay. So if you have not understood what I have written over here, it is okay. So up till now, whatever we have studied, we haven't seen that what time before. You can see this is your T flip flop, and let us assume that input is 1 for this T flip flop, and this is a negative edge triggered T flip flop working in your toggle mode, and this is your clock. Okay, external clock. Now, until now, we haven't discussed anything that how much time before this active edge your input needs to be stabilized so that it has to be considered as a valid input. What I am telling, that we haven't discussed up till now that what time before this active clock edge my input should be stabilized to be considered as a valid input. That means what? If our input was something like this, so see very carefully. So you can see this is your input. Okay, if this is your input, so this is T. So I shouldn't have written it over here like this because I will be using something over here also. So if this is T, what we would have done, if this was T, then Qn, if I assume that initially the flip-flop was reset, the moment we get the active edge, so here we have the active edge, input T is equal to 1. So your flip-flop is going to toggle from 0 to 1 at this particular state. Tell me, is this clear to you what I am trying to say? Is this clear up to this point? That up till now, we haven't discussed anything about your how much time before this edge, before this active edge, my input needs to be stabilized so that it should be considered as input. We have just considered input at this particular clock edge. Whatever was the input, we have taken it like that. If this was, if suppose if suppose this input was something like this, so you can see over here this is the active clock edge, here it is 1, here it is 0. So you can see T input 0 means it will be basically holding the state. So if my past state was 0, if I had initialized with 0, so it will keep on holding the states. Tell me, is this concept clear? Now this is very conceptual thing, so that is why I am asking if you have understood this up to this point. So this was the basic thing that we have seen. Now I am telling you that there is one concept known as what? Setup time. Let me tell you that setup time for this flip flop, it is equal to 1 nanosecond. Now, what do I mean by this? That your flip-flop input is 1 nanosecond. So look over here. Basically, if my input has to be considered as a valid input, then, so I should make you understand it with the help of an example. So this is the active clock edge. And this is your T input, assume. Okay, this is your active clock edge. So here you can see this is t, this is 0, this is 1. Now at this active clock edge, what is the value of t? T is equal to 1. But due to the concept of setup time, this input t will be 1. It will be valid input when this input has been applied 1 nanosecond before this active clock edge. Okay, if it has been applied 1 nanosecond before the clock edge, then you will consider that this flip-flop, it has input 1, or else you cannot. If suppose instead of 1 nanosecond, if this was 0.1 nanosecond, so then even you can see, even at this active edge, you have your input as 1, but this flip-flop is not going to toggle. Why? Because the input has not stabilized 1 nanosecond before the active clock edge. So setup time is basically the time before the active clock edge in which your input should stabilize to be considered as a valid input. If this was 0.1 nanosecond, then your output would have been considered 0. But if this was like minimum, if it was 1 nanosecond, then you will say what? That this is your valid input, t is 1 is okay. So at this particular clock edge, your output will toggle from 0 to 1. Tell me if this concept is clear or not. Tell me, is this clear? So this is the case when our, I shouldn't have written over here. So if setup time is equal to 1 nanosecond. Any doubt, Piyush, Raju? Bhumika has already written yes. Any doubt? Any doubt, anyone? Now see over here. Okay, now see over here. If assume setup time is equal to 3 nanosecond, that means what? For an input to be considered as a valid input, it should stabilize 3 nanosecond before the active clock edge. See very carefully. If this is the active clock edge, now if assume your input is making transition like this. Okay, so this is t, or means I have considered this as so let me assume, okay, this is only okay. Okay, same case. So this is your t, and this is basically 1 nanosecond. So what will be the output? What will be the output? What will be the output? See, first of all, I will tell you that whenever this thing happens, you can see over here setup time is 3 nanosecond. Okay, setup time is 3 nanosecond. And over here, you can see what? That this input is making transition 1 nanosecond before this active clock edge. Okay, before this active clock edge, it is making 1 nanosecond before the active clock edge, it is making transition from 0 to 1. So that means at this particular clock edge, t will not be considered as 1. Why? Because setup time is 3 nanosecond. So the minimum amount of time that is required, means that is required before the active clock edge to be considered as a valid input is 3 nanosecond. But here it is less than 3 nanosecond. So your flip-flop is going to consider this as 0. So if this is considered as 0, we cannot say what will be the next state. Why? Because here even I cannot comment whether if this previous case it was in your, means if I had initialized it with 0, so then it will be 0 only. But if this was initialized with 1, so as you can see, this will be 0 only will be considered. So here then it will be 1. So it will be just holding the value. So I cannot say correctly what will be the state of the flip-flop whenever such kind of condition occurs. Is this clear? That why I cannot say specifically whether it will be 0 or it will be 1, because I don't know whether the flip-flop was initially resetted or set. Okay, is this clear? Tell me, is this clear? Is this clear? See, now one more thing, you might be wondering that this thing, if this is happening, so if we have a register or a counter in which we have multiple flip-flops, okay, so multiple flip-flop, so if this flip-flop, if it has setup time like 1 nanosecond, this might have setup time of 3 nanosecond. No, you cannot have different setup time for different flip-flop either in the register or in the counter. Why? Because your flip-flop, what happens, it is all constructed using what? It is constructed using same kind of material or same kind, identical, you can say. So that is why I was considering over here 0 or 1. So what will happen if these are your similar flip-flop, even if I start from 0 or if I start from 1, basically it will be a cyclic loop. Okay, it will be a cyclic loop if it is a counter. So I will go into the state from which I have started. If I assume 1 over here, still I will be going into the cyclic state. If I assume 0 over here, still I will be going into the cyclic state. But in this case, I cannot determine what will be the state, because here you can see I am not able to determine whether this will be considered as 1 or it will be considered as 0. Tell me if this is clear or not. So that is why here you don't know the condition of the output, what it will be. Is that clear? So whenever setup time you don't know, means setup time is not met, you are not able to tell about the output of the flip-flop. Bhumika, Piyush, Raju, is that clear? Is that clear? Setup time, Piyush?
Actually, if it is present even before setup time, then always we can guarantee that the output will be 0 or 1. But only when the input comes at the time, like here it is 1
Less than setup time.
Always, whenever it is less than setup time, we can't guarantee what will be the output.
Output, yes, very good. Okay,
Okay.
so that is
Okay.
what I am trying.
Thank
Okay.
you.
Yeah. So next, one more concept we have, that is the concept of hold time. Now, what is this hold time? Okay, hold time. So hold time, like here, the concept was before clock edge. Okay, before clock edge, we had to see, means for the input to be considered as a valid input, it should stabilize. In hold time, basically we are more interested in the value of input after this active clock edge. Okay, so look over here what I have written first. Hold time is the minimum amount of time after active clock edge. See over here, it was before the active clock edge setup time, and hold time, it is written time after active clock edge. So this is after the clock edge, setup time was before the clock edge. So hold time is the minimum amount of time after active clock edge during which the flip-flop input should be stable to be considered as a valid input. Okay, So previously, when there was no concept of hold time, okay, then there was no concept of hold time. Okay, so now you can see when there was no concept of hold time, if suppose if this was the T input. So when there was no concept, we were only very much focused on the input part at this particular clock edge. Neither we were concerned before the clock edge or after the clock edge. Particularly at the clock edge, we were concerned that what is our input. So here you can see that T is 1 at this particular clock edge. So if I assume that Qn is 0 initially, so it will toggle at this clock edge. Okay, it will toggle at this clock edge. This was the previous case up till now. But now we have been introduced with hold time. Now what is this hold time? Now hold time is basically the time after this active clock edge, your input should remain stable so that it should be considered as a valid input. If assume hold time over here is 1 nanosecond, okay, if it is 1 nanosecond, so if at this point it is 1 nanosecond, then only this T will be considered as 1 over here and your output will toggle from 0 to 1. But if suppose here hold time is 1 nanosecond and after this active clock edge, your output is transitioning from 1 to 0 in like 0.5 nanosecond, then this T, it will not be considered as 1. Why? Because hold time over here is 1 nanosecond. So basically after the active clock edge, the input should be holded for a minimum amount of time to be considered as a valid input, and that time for which the input is holded, it is known as hold time. Okay, so here if it is your hold time is 1 nanosecond, then you are going to have transition. If suppose we have hold time as 3 nanosecond, okay, if we have 3 nanosecond, but over here the input is transitioning in like this. If suppose input is transitioning from 1 to 0 in like 2 nanosecond. So you can see the minimum amount of time that your input should have been stabilized after the active clock edge. It should have been what? It should have been minimum should be 3 nanosecond, but here it is 2 nanosecond. So here also you cannot specifically determine what will be the state of the output. Okay, state of the output. Tell me if this is clear or not, concept of hold time and setup time. Is this clear?
Hello.
Yes, tell me, Piyush.
In this case, when this 2 nanosecond is less than 3 nanosecond, so we have to write the Qn as don't care.
Yeah, Qn as don't care, because you don't know what will be the particular state, because this input is, you cannot consider it as 1. Okay, you cannot consider it as 1, neither you can consider it as 0. Okay, you cannot even consider it as 0, because you can see this is 1. Okay, this is 1 only. How can you consider it to be 0? Because input T is 1 over here. So it is not like if it is not 1, you are going to assume it 0. You cannot do that. Why? Because due to the concept of hold time, this is not considered as 1. But if it is not 1, you are also even not going to consider it as 0. Is that clear? Are you getting the point?
Yes, sir. Yes, sir. And similarly for setup time also, if that duration is less than that setup time, we have to write Qn as don't care.
Don't care. Yes, you have to write it as don't care. Is that clear?
Yes, sir. Thank you.
Okay. So this is the concept of your setup time and hold time, and there is no more concept. Okay. So now I will give you one of the best question that has been asked regarding hold time and setup time. So solve this question. I am giving you like 2 minutes to solve this question. Okay. Take 2 minutes, think about this question, what is happening, and let me know. So I am giving you 2 minutes. So I am making one call. You can just solve this question. Okay.
You are now unmuted.
So what answer are you getting? Any answers? C. Very good. Anyone else? See, look over here. Look over here. So basically, if you start from this flip-flop, so what is given? In the digital circuit shown in the figure, the flip-flop have setup time of 5 nanosecond and a worst case delay of 15 nanosecond. So all this flip-flop have delay of 15 nanosecond. The AND gate has delay of 5 nanosecond. Maximum possible clock rate for the circuit to operate faithfully. Okay, what should be the maximum frequency? So maximum frequency is actually equal to what? It is equal to, F max is equal to 1 by time period of the clock, minimum time period of the clock that we can have. Now how can we get the minimum time period of the clock? Now see very carefully. Okay, so here you can see R and S, both of them has been given as 1. Now if it is given as 1, that means, so answer me very quickly. If it is given as 1, this means what? This means what?
Both output for both of the first flip flop will be one, always one. It will not fluctuate.
Pardon, I couldn't get.
It will be always one. The outputs for both of the flip flops, the Q1 actually, not the Q bar, will be always one.
This will be always 1. But for RS or SR flip flop, whenever it is 1 1, what did we see? What did we see? When the inputs are 1 1. What did we see? This is very, how is this possible? You guys are forgetting everything. Yeah, so this is the place. Look. Are we getting this? For SR flip flop, 1 1 means invalid state. So first of all, let me tell you that this question was actually wrong. Okay. So they have made a slight mistake over here. So they should have written actually JK flip flop every place. JK, JK, JK. Okay. Because when you put SR equal to 1, SR equal to 1, it is basically what? It is working in your invalid state. Okay. So this was wrong question. I will not be making corrections over here. Then your diagram, it will become very messy over here. So it's okay. So first of all, this thing needs to be cleared. That means you guys also should have asked me, sir, here RS is equal to 1. So we are working basically in invalid state. So the question should have been what? It should have been JK flip flop. Okay, fine. So that is a silly mistake. So now look, in the first flip flop, you can see this is the clock. Okay, clock is over here. And same over here also, we have the same clock. Sorry. So here we have the clock. So listen very carefully over here. And here also we have the same clock. Okay, same clock. Now, if you see over here, basically, we are starting from here. Okay, third flip flop. Now, why I am not starting from here, I will tell you. So look over here. In the third flip flop, for any input, okay, for any input, you can see basically this is the clock and they have given setup time of 5 nanosecond. So setup time is basically what? It is the time before the active clock edge. So I am starting from here. Okay, I am starting from here. So that means 5 nanosecond before this active clock edge, my over here, all the input should have stabilized. Okay, input should be stabilized over here due to the concept of setup time, 5 nanosecond. Are we getting this? Why I started from here? So this is one of the active clock edge. This is also one of the active clock edge. Now setup time, it is before the active clock, means setup time is the concept of input stabilization before the active clock edge. So that is why I am taking this, because if I take from here, then how can I go over this side? Okay, because this is not before, I have to go over this side, so this is after. So this would have been the concept of hold time if I start from here. So that is why I am starting from this clock edge. Why? Because setup time is the concept that actually relates what stabilization of input before the clock edge. Okay, before the clock edge. So you can see this is what 5 nanosecond. This should have stabilized. Now why I didn't start from here, I will tell you. So look over here. So 5 nanosecond is required, means all the input should be stabilized. But you can see this T is equal, means R, or over here if you have to write, you can even write J over here, whatever you want to write. This input is already available from T equal to 0. This is already available from T equal to 0. That means it has stabilized by 5 nanosecond. But what about this one? When are you going to get this input? So this input actually we are getting from this AND gate, and here they have asked actually maximum possible clock rate, maximum possible rate. So in that you are going to consider that all of the flip-flop, AND gate, everything is getting what? Everything is getting your delay, because worst case we will be calculating. So for calculation of worst case, if I assume that this AND gate is also suffering from delay, so that means this input we will be getting more after 5 nanosecond. Okay, after 5 nanosecond more. Okay, so this will be what? This will be 5 more nanosecond. Now come over this side. Okay, come over here. So here you can see one of the input of this AND gate, it is coming from here, and another input is coming from here. Okay, so I will be clearing up the diagram a little bit. So one input is coming from this flip-flop, another input is coming from this flip-flop. Now tell me, after how much time will this input be produced? See, now why didn't I take the concept of setup time over here? Because you can see that this 1 nanosecond, listen very carefully, this 1 nanosecond, it has been applied from T equal to 0. So already it had been stabilized from the beginning. So I didn't have to worry about setup time. But here in this case, one of the input was depending on this output of the AND gate. So that is why I was worried about what? I was worried about setup time, that it might transition over here. If this was also fixed from your T equal to 0, I wouldn't have worried about this setup time. So here, that is why I am not worried about setup time in this 2 flip-flop. Why? Because already the inputs are fixed from T equal to 0, and you can see the concept of hold time, setup time, it only comes whenever there is a transition in the input. Look, here also we made a transition from 0 to 1, 0 to 1. Here from 1 to 0, 1 to 0. If there was no transition in input, there will be no concept of setup or hold time. So that is why I didn't consider setup time in first flip-flop and second flip-flop. Now you can see that if suppose at T equal to 0, I give this input. So after 15 nanosecond, output will be produced, this Q0. So we will get this after 15 nanosecond. But you can see what? That basically this is the clock for this one. this second flip flop. So this clock, it is taken from the non-complemented output. So that means after 15 nanosecond, this will be produced. So after 15 more nanosecond, I will be getting this output. But by that time, this means this input, it has already stabilized because it was available at t equal to 15 nanosecond, and this input is available at t equal to 30 nanosecond. So that means this much time, it is what? This is 30 nanosecond. So in total, how many nanoseconds between two active edges? So 30 plus 5 plus 5, so that is 40. So this is the, you can say this will be your minimum time or minimum time period of the clock whenever there is worst case delay or setup time. So 40 nanosecond. So now if you want to calculate the frequency, so that will be 1 by 40 nanosecond. So this will be 10 to the power minus 9, or I can write this as 1000 by 40 megahertz. So this will be 25. 25 megahertz is the correct answer. Option C. So Bhumika, very good. Okay. Tell me if this concept is clear or not. So this is a very, very good conceptual question. And in EC electrical IN, I haven't seen any other question of setup time and hold time till your 2018. Okay. 2018, there was no question. In CS, there is one question. I have to check for 2019 and 20 question once. Okay. Because there was one very good question, but I couldn't actually get it. Okay. I couldn't get it. So I will be searching for that question also. And Raju, you had sent me one question, okay, of setup time and hold time. So I want you guys to do. So I will be forwarding that question in the group. So is the question complete or what? Consider the following. Yes, it is complete. So I will forward this question in the group. Okay, I will forward this question in the group, and I want all of you to solve this question. Okay, I want you to solve this question as your homework. First, tell me if you have understood this question or not. So this is one of the best question asked. If you are able to understand this question, then you will be able to solve any question of your propagation delay and along with your hold time and setup time. Tell me, is this clear? Is this clear? So instead of setup time, if they had said hold time over here, hold time. So then what would I have done? I would have started from this point, 5 nanosecond, because hold time is the concept of input stabilization after the active edge, after. Okay, after. So that is why I would have started from here, 5, and then I would have shown 30. Okay. So if it is setup time, I always start before the active edge. So here if I had taken before, so then also I would have to take one more clock cycle, something like this. So if I had started, so here also concept will have been means it would have been before this edge. So I will have to go from right to left whenever it is setup time, and from left to right whenever it is hold time. Tell me if this is clear or not. Is this concept clear? Is this concept clear, everyone? So now, one more, Raju, you have something you want to ask? So now, basically what we have the consider of race around condition. Can anyone tell me what is this race around condition, or what do we mean by this race around condition? What is this race around condition? What is race around? Okay, fine. So we have seen basically that whenever J and K input, both of them are 1, what happens? My output, it toggles. Okay, it toggles. So that is known as what? That is known as toggling state. So everywhere until now, we have seen what? We have seen edge triggered flip flops. So in edge triggered, there is only one place where your triggering will take place or where your toggling will take place in case of when j and k equal to 1. But what happens if we have level triggered? In our case, let us assume it is positive level triggered JK flip flop with both the inputs as 1. So this is your clock. And let us assume that this flip flop has propagation delay, finite propagation delay del t. Okay, it has finite propagation delay del t. Now listen very carefully. What I am telling, that now we have this JK flip flop as your positive level trigger flip flop with j equal to k equal to 1. Okay, so now how will that output look? So look, this is positive level, so only the output is allowed to change in this positive levels. So now look, if I initialize this flip flop from 0, see very carefully. So now if we start from 0, what will happen? After del t time, because there is a finite amount of delay, so after del t time, it will transition to 1. And again after del t time, this is going to transition back to 0. Why? Because this is here in this positive level, the flip-flop is allowed to change state. So continuously it will toggle. Now if suppose there was this propagation delay was 0. So what will happen? As we have feedback over here, so continuously what will happen? I will transition from 0 to 1, 0 to 1 like this. Continuously. Means we cannot even see, it will be like this only. Continuously we are transitioning from 0 to 1, 0 to 1, 0 to 1, 0 to 1. Continuously this will happen up till this point, and after this point we cannot say what will be the state because we don't know what would have been the transition. But it is better if I take a finite amount of propagation delay. Okay, so now you might be thinking why this is happening. So I will even show you, don't worry. So if this is, assume j and k equal to 1, and we know what this is, your NAND latch. So this will be set bar and this will be reset bar of the latch. Okay, this will be set bar and reset bar of the latch. So now if you assume that initially qn equal to 0, so if that is the case, so this will be 0 over here and this will be 1 over here. So if one of the input is 0, if one of the input of NAND gate is 0, this will be 1, and obviously this is means you can see all the inputs over here are 1 1 1. At the positive level of the clock edge, everything will be 1 because clock is also 1. This j is 1, and even I have shown you that this feedback will be also 1. So everything is 1. So this will be what? This will be 0, this will be 1. So what will happen? You can see if set input is 1, immediately this will become 1 and this will become 0 at del t. So this is becoming 1 at del t. Fine. Now look, when this is 1, so this one will be feedbacked over here. So now we have 1 over here. And if this is 1, obviously over here we will be having 0. And you can see k input is 1, clock is 1. So this time this will become 0 and this will become 1. And when set input 0, reset input 1, immediately after del t time, so in total 2 del t, this will become once again what? This will become 1, this will become 0. So after 2 del t time, once again this will become 0. Okay, so now this cycle will keep on continuing, so on and so forth. like this. Okay, it will continue up to this clock edge. Now we cannot determine what will be the state. So this is actually known as what? This is known as your what? Race around condition, that continuous toggling will take place. Now if you decrease the del t, so what will happen? Basically this toggling will be also very, very significant. If you decrease the del t, okay, it will be like this. Continuously it will be toggling. Okay. Is this clear? The concept of race around condition? Please tell me yes or no. Is this clear? So if we increase the clock edge, means if we increase the del t, your time period will increase, or the number of transition will decrease. And if we decrease the delay time, our transition is going to be very much increased. Is this clear? Tell me yes or no. Is this concept clear? Piyush, is it clear to you? Now, when it was, if this was your edge triggered flip flop. So in edge triggered flip flop, we know what? That basically what? Our output is allowed to transition only at the active clock edge. If there is del t propagation delay, and if we are starting from 0, so after del t time, this will become 1. And once again, after del t time, this will again transition from 1 to 0. Okay. So if this was active edge triggered flip flop, then your output Qn, it will look like this. Is this clear concept of race around condition? See, when I was in my BTech, I couldn't understand what is this race around condition, because our professor, he told us what? That race around condition, he draw this diagram and then he drew this one and he told us this is your race around condition, like this transition is happening. He never told us why this is actually taking place. Okay. So now tell me, I don't want to be that kind of a teacher. So you should tell me whether you have understood or not. Did you understand? Okay. So now let me ask you, why is this continuous transition taking place? Why is this continuous transition taking place? For what? Means I should be reframing my sentence. For exactly, I'm not able to tell. Okay, so in this circuit, why is this continuous transition taking place? Due to what part in the circuit? Now remember, first, we started from SR flip flop. Okay, from SR we went to D flip flop. Okay, D is basically delay, we know. And to remove one of the main drawback of SR flip flop, we went to JK flip flop. What was that positive aspect of JK flip flop? Tell me. Bhumika, Piyush, Raju, anyone? What was the positive aspect or the positive thing of JK flip flop which actually eradicated the negative aspect of SR flip flop? What was it?
Indeterminate state of SR was removed in JK flip flop.
How did we remove it?
By connecting the outputs of Qn bar with J and Qn with K.
Okay, so basically you are connecting the output with the inputs. Okay, so with the help of that, you actually removed that negative point. So when we connect output to input, what is that process known as?
Feedback.
Very good. So the previous thing which was acting as a boon, now it is becoming a bane. Okay, so now that feedback is actually causing this continuous multiple transition. You can see why? You can see this 1, it has been feedbacked over here. So again, it became 0. Now this 0 will be again feedbacked over here. Okay. This continuous feedback is causing this race around condition. So always remember in life also, if something, it is a boon at this moment, it doesn't mean that in your entire span of the life, it will be a boon only. It might become a bane also. Okay. So you can see the same thing which was actually solving the problem at that very point. Now it is creating problem for us. Okay. It is creating problem for us. Now, can you suggest me any such means method with the help of which we can actually avoid this race around condition? Now don't tell me, sir, we will remove this feedback. Then this will not be JK flip-flop anymore. This will become again SR flip-flop, and we know basically what are the problems of SR flip-flop. So we cannot do that. So tell me some of the method with the help of which we can actually remove this race around condition. Think about it. Think. So such kind of thing will be asked if you go into IISc interview. Okay. So even if you don't know, like the way I brought out the answer from you guys that tell me from where race around, they will give you hint. You have to catch those hints. Okay. So in any interview, you go for IIT or IISc, in PSU also. PSU usually they don't help you that much because there is very less time. But in IIT, IISc, they will always actually give you small hint to get the answer out from you. So now tell me what plans or what method you suggest to remove this race around condition. Now don't tell me, sir, we will be using master slave flip flop. Okay? No. So if you know about master slave, that is fine. I want some other things. Okay? So tell me, by looking in this circuit, what can you do? अरे कुछ तो बोलो, say something.
If that clock pulse for that which duration the clock is high, that pulse is high, if we can reduce it even less than propagation delay, then it can be something.
Okay, so you are telling that this positive level should be decreased. You are telling me that?
Yes.
So something like this, you are telling me, sir, if we do something like this. Okay, if we do something like this, then sir, we can do what? We can avoid the race around condition. Why? Because we have decreased this positive level duration. So how many of you are from electrical? Nobody is from electrical. So this is actually known as, I don't know if you might be knowing this term, decreasing the duty cycle. How many of you know this term duty cycle? So now if I told you, so duty cycle, it is equal to, this is your T on, and from here to here, this is T off. So time period of the clock is equal to T on plus T off. Now why have I considered this as on? Because during this time, your flip-flop, it is getting transition. So I have assumed it to be in on state. And in this much time from here to here in the negative level, I have assumed to be off. So duty cycle is basically T on divided by T on plus T off. So you are telling me decreasing the duty cycle. So decreasing the duty cycle means what? If we decrease T on and increase T off, my duty cycle will decrease. So that is what you suggest. So this is one method you can do. Okay, change the duty cycle. So this can be done. This can be done. Okay. Next method, anything else? Next method, anything? See, what we can do, if I decrease the time period of the clock itself, if I decrease the time period of the clock, decrease time period of clock. But tell me, is decreasing the time period of clock, is that a feasible option? Tell me, is it a feasible option? It is not feasible. Why? Because then the clock frequency will increase. Okay, clock frequency will increase, and in any digital circuit, even in your laptop, okay, in your laptop, the clock frequency is always fixed. Okay, it is always fixed. It is not like there is some different clock frequency in some of the circuit and different clock frequency in some other places. Okay, it is not like that. Clock frequency always remains the same. So we cannot even do that. Okay, we cannot even do that. Third, so this is not feasible. Okay, not feasible. What about this one? What about this one? Oh, sorry, means I had thought. So I am asking, any other method you have? Any other method? So you might be saying, sir, what if we increase the propagation delay itself? Means like something like this. Okay, means we have increased the propagation delay very much. Tell me, is that a very good thing, that increasing the propagation delay? Increase del t. So that is also not feasible. Why? Because then our circuit or the operations are going to become very slow. Okay, operations are going to become very slow. Okay, so the most important thing now I want. Okay, so you guys are not from electrical, so this might, it is not actually means what I should be saying. You guys might not be knowing. So any one of you know this, that what happens when we differentiate a square signal? What happens when we differentiate a square signal? You guys know this? Anyone? Okay, fine. So this point is only for electrical people. If you guys don't understand, it's okay. So use a differentiator. Now differentiator, if you guys are from CSE, it's okay. No need to copy, no need to understand. But I know few of the students are missing today, so for them only I am telling this. So they might be knowing that differentiation of step signal. So these are step signal. No need to understand. Okay, for CSE people, no need to understand. So basically, these are your steps, combination of step signal. So combination of step. So these are your ideal step signal. So practically, if I differentiate it, so it will look something like this. So differentiation of step is what? It becomes your impulse. Okay, so basically what we have done, we have decreased the duty cycle very less. So there is no more clock edges over here. It is a very small time, very small time. Let me write it as del t dash. So this del t dash is very less compared to del t. So what will happen? Transition will only take place one time in this very small positive level. So we use differentiator and we construct a differentiator using RC circuit, first order low pass filter. Okay, so this is your first order low pass filter. Okay, so this is your RC circuit. So CSE people, this is not for CSE. Okay, So these three are your, you can say what means, its exact term I am not, ad hoc, I guess. Yes, ad hoc method. Yeah, in Hindi we usually say what, jugaad. So it is kind of those method that we can employ over here. So actually, why did I ask you guys? Because this same thing was asked to me in IISc, and the only method that I could say it was this, because I was from electrical background, and in every textbook only this was written. These three were not written. Okay, so one of the professor, and a professor, some DVS Murthy or some SV Murthy, I exactly don't, Murthy I remember, he told me all this method. Okay, and means he was also laughing, I was also laughing, because I was giving my interview in Hindi. So I told him, sir, I don't know all these methods. Okay, so he was laughing, like, you should know, these are all very basic thing. Okay, you can do like this. So the only method I knew, it was this method. This three method I knew from them actually. Okay. Okay. So now this is what. Okay. So I will tell. So basically all this method, these are not feasible method. Why? Because either you can see we are changing the clock. Okay. We are what? We are changing or manipulating the clock, or we are manipulating the circuit, and we are making it a, means we are adding something in the circuit, or we are increasing the propagation delay, which is a negative thing in a circuit. In a circuit or in a digital logic, we want all the elements to have the least amount of propagation delay, but here we are actually increasing. And if you are from electrical background, basically R and C, they are very bulky component. Resistor and capacitor, they are very bulky components, and digital circuit, they are very compact. So we are not going to use this. So we have some method, and that method is what, master slave flip flop. So I want all of you guys to very quickly copy this down. Copy this. I will be back in like 1 minute. Okay, so copy this circuit. So did we copy this circuit? So this is basically the construction of master slave flip flop. Now, how is this master slave different? Let me show you. Okay, so first let me ask you, what was the problem due to which we had this race around condition? It was due to this two feedback. Okay, this two feedback that we have, it was actually causing what? It was causing the race around condition. Now, what we did, basically you can see, so see very carefully over here. This was actually the JK flip-flop. If we had connected this feedback path over here and this feedback path over here, we will be getting the JK flip-flop. So what we did actually, we have removed those flip-flop and we have connected one set reset latch over here. You can see SR flip flop, this combination. This is your SR flip flop. This is SR flip flop. You can see. Okay, this is SR flip flop. So now look very carefully. We are actually taking the feedback from the output of this SR latch. Okay, output of SR latch. Now look the circuit very carefully. I will be explaining it to you. So this part, okay, this part, this is known as your master part, and this part is known as your slave part. Okay, this is known as your slave part. This is master, this is slave. Fine. Can you analyze this circuit on your own? Now one more thing. These all the flip flop, they are basically level triggered flip flop, level triggered. So this is the clock. You can see master will act in the positive level. So I have actually done what? I am assuming that master is a positive level flip flop, and slave, it will work in your negative level. Why? Due to, you can see over here, I have added one inverter. So master will be active in the positive level and slave will be active in the negative level. Okay. So now if you put J equal to 0, J equal to 1, K equal to 1, and we are in the positive level of the clock. So what I will be doing, is this diagram visible to you guys? Please tell me yes or no. Is this visible properly? Okay, fine. So now I will be drawing the clock. So clock, okay, fine. Okay, so remember, master will be active in this part and slave will be active in this part. Okay, so now look, when we give J equal to 1, K equal to 1, and we are starting from this point, assume we are starting from this point. Okay, so initially, or you can assume initially all the states are 0, 0. First I want you guys to make one transition yourself, then I will be showing. So assume initially that Q is equal to 0. Okay, if Q is equal to 0, then what are you going to get? Okay, initially assume Q equal to 0. Now what is this Q? So Q, if you want to see, so let me assume that this point is Q, and let us assume this point is, let me take Y. Okay, this is Y, this is Q. So now initially let us assume Q0, Y0. So Q0, Y0. Instead of writing for this and this, I am not writing. So this is Q, this is Y. So Q is actually what? Q is the output of this JK flip flop, and Y is the flip flop of this, means output of this latch. Okay. So now tell me what is happening over here. So if this is Q, remember this is your NAND, what? This is your NAND flip flop. Okay. So now if this is Q, so let me just give me a minute. So this will be your, if I am assuming this to be as Qn plus 1, so obviously this is going to be reset and this is going to be set, because this is your NAND flip flop, SR flip flop. Okay, so in SR flip flop using NAND, this is the case, and this is what? If this is Qn plus 1, so obviously this is going to be what? This is going to be the set of the latch, and this is going to be the reset of the latch. Tell me if this is clear to you guys or not. Is this clear? Or even if this is not clear, it's okay. Means we will be deriving it, why to make the circuit complex. So let us assume this Q is actually 0. Okay. If this is 0, how are you going to start the circuit? Q0, Y0. So look over here. First case I am showing. So if Y is equal to 0, that means what? This is 0. This will be 1. So if this is 1, so this 1 will be feedbacked over here. Okay. And this 0, it is going to be feedbacked over here. So now, if this is all the inputs are 1 over here, so this is 1, this is 0. Okay. So if this is 0, immediately this will become what? This will become 1. And if this is 1, this will become 0. See, any problem in this? Any problem? Tell me if there is any problem. Any problem? So look very carefully. So when I started the circuit, Q is coming out to be 0. See? Please tell me yes or no. This is very, very conceptual. If you are not able to understand, then please let me know that, sir, we are not able to understand.
Hello?
Yes, tell me.
After the NAND gate to which J is connected, the wire which will it will be having 0, no?
Why? Means which one? Wait a minute.
Just after the NAND gate which is actually connected to J,
Okay.
the output will of that NAND gate will be 0.
Yes, sorry. So this is 1, 1, 1. So this will be 0. So this will be 0. And here this will be 1. So if this is, if this input is 0, okay, and this is 1, so immediately this will become what? Sorry. So this will become 1 and this will become 0, because if one of the input of NAND gate is 0, immediately it becomes 1. So Q is 1. So Q is becoming 1. Fine. So look, now this one is actually what? This is the input of this SR latch. So this is 1, this is 0. But in this much duration, so this will remain 1. This will remain 1 because there is no more transition in this place. There is no feedback. Look at this much time. What is happening? This is a negative level triggered flip-flop. So here you can see this is positive level. This is the clock. And only master is active over here. Slave is inactive or slave is in hold state. So initially I have started with 0. It will remain at 0 up till this point, and this will be 1. Okay, this will be 1. Now look what happens in this particular time when we hit the negative level. So at this particular moment, this is 1, this is 0. If this is 0, this becomes 1 and this becomes 0. Okay, this will become 0. Why? Because you can see, wait a minute, why will this become 0? So 0, 0. So you can see negative level of the clock we have. So basically we are getting 0 over here. So this will be 0. So 0 means this will be 1, 1. And whenever in NAND gate we have 1, 1. So whenever we have 1, basically what will happen?
Hello.
Just wait a minute. So have I made...
After inverter, it will be 1, I guess.
Yes, sorry. See, basically this is in the negative level. So in the negative level, clock is 0. So this will become 1. So that is why I was thinking what mistake I am making, because there should have been a transition. So this will become, clock will become 1. This is 1 and this is 0. If this is 0, this will become 1 and this will be 1 into 1. So this will become 0. So now immediately if this becomes 0, so what will happen over here? We will be getting 1 and here we will be getting 0. So y is making a transition from 0 to 1 in this particular time. But what about master or Q? So during this time, you can see it is the negative level. So in negative level, clock pulses will be 0, means 0 for this one. So it will hold the state. So this state will be holded. So this state is going to be holded over here. So now what? So the next state over here we have is 1 and this is 0. So I should use some different color, so then it will be very good over here. So let me use black. So now we have is 1 and over here we have 0. So now you can see once again this one, it will be feedback over here. So this will become 1 and if this becomes 1, this will become 0. So once again you can see if this becomes 0, immediately this will transition to 1 and this will transition to 0. If this transitions to 0, this will become 1 and if this becomes 1, so this will become 0. So at this particular time, once again this will transition to 0 like this. Okay, and during this much time, when master is active, slave will be actually holding the value. So this will go like this. Now look what happens when we once again encounter the negative level. So in the negative level, already this has been given 0, 1 and clock is again 1 over here. So if this is 0, this is 1, what will happen? This will become 1 and this will become 0. Now if this is 0, this will become 1 and this will become 0. So once again you can see this y will transition from 1 to 0 and this will continue to be in 0. And once again when we have one more clock over here, so let me draw that also. So you can see this will keep on going like this. Okay, so now you can see what, sorry, yeah, so this is okay. So now you can see what, that basically this flip-flop, this is the output of the whole master slave flip-flop. So this output, you can see it is only transitioning at this particular edges. You can see at here it is making a transition, y is making a transition from 0 to 1. Okay, and once again whenever at this negative edge, it is making a transition from 1 to 0. So you can see we have actually solved the problem of this race around condition and we have constructed this level triggered flip-flop same as your negative edge triggered flip-flop, and this is known as what? This is known as your master slave flip-flop. Tell me, is this clear? Is this clear? Tell me yes or no. Did we understand the concept of master slave? Bhumika, did you understand? Piyush, Raju? And Raju, why do you use your mobile to watch the lecture? It's good actually if you use laptop, okay, laptop or computer, because in big screen it is actually easier to see. You don't need to strain your eyes. Okay. So did we understand this concept of master and slave? Okay, it's okay. So you can see basically in this circuit, master, we are naming this as master, but it has no importance. Okay. The slave is actually the output of the circuit. Okay, so even in a country also you can see, means country, it is the decisions are taken by the country head, but the country is run by its workforce. Okay, workforce. So a
Hello.
country is run by its workforce. Yes, tell me, Piyush.
I guess the master slave nomenclature would have been given because the queue is actually having the output first, but only Y is having the same output only after few delay, after the delay of the master flip flop. That's why it actually might
Yes,
have been given.
yes,
Because the
master and
slave is actually following the master only after
master,
the propagation delay.
certain amount of propagation. And what is that propagation delay? You cannot say propagation delay over here. What is that particular thing you will be saying? So this would have been my next explanation, what you just said. See, basically this is what, this is the output of the master and this is the output of the slave. So there is, means basically the slave is following the master. Okay, slave is following the master, but after a certain amount of delay. And what is that delay? Basically it is your half clock cycle, TCLK by 2. Can you see that now? So you won't be saying it as a delay. Delay is something else. You will be saying that the slave is following the master at an interval of half clock period. Is that clear? Is that clear? So I find actually this master and slave a little bit means funny. Okay, means you only think the first person who might have actually invented this circuit, he or she might have written master slave. So I don't know how, what means, what is the, they could have even written like in, you could have even written a follower flip flop, Anna. So this would have been a follower flip flop, you could have written like that. So any else other term you could have written master slave. So it's okay. It's a lot of things are there and even scientific things also. So with this, finally with this concept, we cover your sequential circuit. Sequential circuit. Now one more session I will take particularly for problem solving of sequential circuit, in which I will be taking questions of EC, electrical, IN and even CS. So Piyush, I was asking yesterday for that website. Okay, so basically we had solved that question, if you remember. One day I even told that question was very good. I don't know where is that question.
I have posted the link for that question.
No, not that one. Means I told I haven't seen that question ever in my BTech life or in my career. If you remember. I don't exactly remember what was. No, not this one. Not this one.
Sir, actually, this is not the second one after this one.
Yes, one. This one only. Yes, I was searching. Means I was continuously searching for this question and I couldn't find it. So it's okay. It's okay. So I will be taking questions from here also. Okay. So let me plan that circuit, means question, that session. So today, what we will do, we will end the session over here. So we'll be complete sequential. In your Thursday's class, we will be completing your this thing, that combinational part. Okay, combinational circuit. We have few topics left. One very good question also. So this question was left, and few, this encoder, decoder, tri-state buffer, all those things were actually left. So we will be finishing this and then your syllabus will be complete for CSE, guys. Okay. So Friday I will be keeping class only for EC and electrical guys. You guys don't need to come. So the next class for you people, it will be on Thursday. Okay, Thursday from 8:30 or 8:50. At what time you guys want your class? 8:50 or 8:30? 8:50. So that is okay. 8:50 is okay with me, no issues. So we will have the class 8:50 then, and we will cover this topic, and we will be solving more questions of combinational circuits. So you can consider it as a test. We will see more questions from combinational circuit. Okay. So revise combinational circuit and come, and then we will have one session for your sequential circuit, and then one more session for all the remaining topics. Okay, all the remaining topics that we have, like Boolean algebra and that what one's complement, two's complement, and all those things. Okay, whatever is left, all those things we are going to see the questions. Okay, so is that okay with you guys? And Raju, you will be covering all other topics that is left. So next
Hello.
class, yes, tell me.
Uh, I have a doubt that for what purpose this master-slave network, master-slave flip-flop are being used. Like for normal flip-flop, we can understand that we can use it for counters, and there are many other switching where something like switching purpose we can use these flip-flops. But what is the use of master-slave flip-flop?
Okay, let me ask you one thing. Tell me one thing. Means, so on note this. Okay, first note this. Thursday we have the class from 8:50. Means 8:50 p.m. Okay. So okay. Now let me ask you one question. In real life, okay, in real life, do you think first of all, can we create one exact square wave, something like this? First, let me ask you this.
Never.
Never, you cannot construct. Why?
There is actually I learned it somewhere, some Gibson approximation, something like that. It is there, which actually exactly sketches the errors. Yes, Gibbs, this one. So there will be some 99.9% accuracy, and rest all will be not very
Yes,
much
very
proper.
good. Very good. So I will explain now. It's okay, you know. So if you guys might have heard about Fourier series. Now I don't know. I don't expect that you guys might have heard. So according to Fourier series, any periodic signal, it can look like this also. So this clock cycles are basically periodic. So this is also one periodic signal, okay, triangular waveform. So any periodic signal, even a sawtooth waveform, so this is triangular, even if you have a sawtooth waveform, something like this, periodic. So any periodic signal, you can represent it with a set of orthogonal signal. Now I won't be going in that much depth. A set of orthogonal signal. Now what is orthogonal signal? What you want to say
Mathematically.
something?
Uh,
What?
yes, actually, this square wave is sum of infinite sinusoids.
Yes, I will be explaining. Just give me a minute. So basically, what is orthogonal signal? Orthogonal signals are those signal that for one time period, if we take the product and integrate it, it will be zero. So one such set of orthogonal signal is your sine n omega naught t, cos m omega naught t for the values of n and m discrete. Discrete means what? From 0 to infinite, means not 0, from 1 to infinite. So this is basically is what Fourier series, that if we have this square wave denoted by xt, so I can denote this xt as a naught plus a1 cos omega naught t plus a2 cos omega naught t, like this till infinite, plus b1 sine omega naught t plus b2, I'm very sorry, 2 omega naught t, b2 sine 2 omega naught t, like this b3 sine 3 omega naught t, and like this, so on and so forth. Now what are this omega naught? So omega naught is actually the fundamental frequency of this signal. So if this is your time period, fundamental time period, so then omega naught is equal to 2 pi by t naught. Okay, 2 pi by t naught. And you can construct the square wave using combination of sinusoidal. So what you can do, one of the sinusoidal, it will look like this. Fourier series. So drawing this without the help of MATLAB is little bit difficult, okay? But still I will try. So one of the sine wave, it might look like this. Okay. Another, it will look like this. One more we will have. So when we take all this combination of sinusoid, basically this square wave, this is your ideal square wave. This ideal square wave, it looks something like this. So let me once again draw the ideal square wave. So this is your ideal square wave, but in practical life, this square wave, it looks something like this. So it is actually very difficult. Please forgive me for my diagram. Okay. So it looks something like this. So you can see at all these edges, at all the edges, wherever there is discontinuity, there will be overshoots. These are known as overshoot in electrical engineering. Okay. So these are overshoot, or there will be maximum error. So basically, there is no such concept of edge triggered flip flop. There is no such concept of edge triggered. Edge triggered flip flop are basically your ideal cases. Any flip flop you take, any flip flop, basically it will be kind of a level triggered only. Level triggered. There will be some concept of level triggered. So due to this concept of level triggering only, we are getting this concept of setup time and hold time. Okay, we are getting this concept of setup time and hold time. Why? Because all the flip flops, they are not ever your edge triggered, because even at this edge your output can change. But if we have the concept of stabilization, that means basically we are taking a level. See over here, the duration of the level is 1 nanosecond. Here, as this criteria is not met, so that is why we are saying input is invalid. Over here, the criteria of the level to be maintained or the level to be stabilized is once again 1 nanosecond. So that means what? In practical cases, any flip flop you take, it has a minute level triggering only. There is no such case as your edge triggering. So for that only we have this master slave. So in any package you take, if you have a JK flip flop, basically you get the combination of master and slave only. But it is like that only. If in the first class only, if I had explained you that all the flip flops are actually constructed using this configuration, you might have got confused. So that is why when we are learning something, we keep the concept very simple and then gradually we increase the concepts. Okay. So this was the highest level of concept that I had to give you. And remember, all the practical JK flip-flop are constructed like this only. You won't be seeing any JK flop like this. Okay, because even if you take an edge triggered, there will be actually some level triggering in that, because you cannot construct a perfect edge. Okay, you cannot construct a perfect edge. You can look over here. There is some level over here. Okay, there will be some level of this edge. Did you understand the concept?
Yes, sir. But actually, there are like SR and D flip flop, T flip flop. So, is that possible that if we have master slave T flip flop or SR flip flop, something like that, only master
See,
slave JK flip flop is possible?
no. See, JK flip-flop is the most versatile flip-flop that we have. Why? With the help of JK flip-flop, I can construct D flip-flop. With the help of JK flip-flop, I can construct T flip-flop. With the help of JK flip-flop, I can construct what? I can construct even SR flip-flop and remove the negative aspect of SR flip-flop. So basically, you can say like this, that JK flip-flop is the universal flip-flop. Okay. Now look, if you have D flip-flop, you cannot construct JK flip-flop using D. Okay, means you can construct by some like if you have inverters and all those things, you can construct. Okay, but with the help of JK flip-flop, without any additional, what I can say, additional hardware, you can implement all other flip-flop. So that is why JK flip-flop is actually what? It is the universal flip-flop that we have. Okay. Did we understand, Piyush? Yeah.
Yes, sir. Yes.
So,
Thank you.
any other thing you guys wanted to ask? And Raju, you are going to see all the sessions that are left. Okay. So please complete those sessions. Okay, then I will be ending the session here only. Okay. So Thursday, remember, from 8:50 we have the class. Okay. So I am ending today's session then. Recording on, because others might also have this problem. So we have A N, B N, C N. So we have to check for KA, na? KA you want me to check. So 0, 1, 2, 3. 0, 1, 2, 3 is don't care. 1, 2, 3, 4, 5, 7, 6. So 0, 1, 2, 3 is don't care.
Sir, the placement of 2 and 3 are incorrect.
Oh, batao. So 3, 2. Okay, fine. So next what we have don't care at 6 and 1 at 7. We have don't care at 6 and 1 at 7. So this will be like this. Okay. So this is 0, 1. So you can see this will be Bn. So this is correct. Sorry, we had actually written this for Ka. So Ka is equal to Bn. Yes, this is correct. Okay.